Hi guys, this is Weird Math, Chemistry Edition. Okay, so this is actually quiz 11M. We're going to look at in quantitative analysis. This is the quiz's practice for the quiz that we're going to have tomorrow. So I have a couple of observations that I wanted to share with you about how he writes out his problems and how to know what to do with the information that you have. Okay, so let's look at it. Consider the diprotic acid H2Z that reacts with water, and it gives you the Ka1 and the Ka2. The first thing that you're going to need to do is you're going to need to write down the pKa1, which remember, that's going to be just your pK1 and for this. All right, and then pKa2 is going to equal pK2. So calculate that. That is step 1. Now, let's look at the actual wording of the problem. And I will make another video where I actually go back in and solve these, but I just wanted to talk about how to figure out which one of these equations that you need to use. Okay. So for part A, we are looking at NaHZ. Okay, so if you look at our reactions here, when this dissociates, it's going to be Hz minus and Na plus. So the sodium is a spectator. It's just going to not react, and you can just pretend like it's not even there. All right. But Hz minus is both in Ka2 and Ka1. So when he says you've got 0.049 molar of NaHC, and he wants to know the pH, he is wanting you to use this lovely new equation that we learned, which is the pH is 1/2 of pKa1 plus pKa2. So if he gives you the intermediate, and that's what this is, Hc minus is the intermediate species. All right. And so this one, if you'll remember, can be an acid or a base. And so you have to treat it a little bit differently than you do the H2Z or the Z2 minus. All right. Now, the second section, part B here, you've got a solution containing 0.049 molar of Na2Z. So when this dissociates, you're going to have the Na plus, you're going to have 2 of those, and then you're going to have 1 Z2 minus. All right, now we've already said that sodium just does not react in this. It just kind of exists as a salt. You can pretend like it's not there. All right, but what you're looking at is the Z2 minus. This is part of your second step, your second reaction here for the Ka2, and it's wanting the pH. So your first step here is you're going to go from your Ka2 and you're going to find what your Kb is. Now, if you'll remember how these equations work, Ka2 times Kb1 is going to equal Kw. So you're going to solve to find Kb1, and then you're going to feed that in to your Kb right here. You just replace this with Kb, but it's the same equation, but you're going to find out what your concentration of hydroxide is, and then use that to find your pOH, and then go from pOH to hydrogen ion concentration, and then a pH, or pOH 14 minus pOH is pH. Now, question C. The pH of the solution containing 0.49 molar of H2Z. So with this one, we had to go Kb to find OH, and then pOH to find pH, right? With this one, we're actually looking at the first equation, and so when we break that apart, we've got H plus right there. So then we're just going to do Ka1 is equal to the concentration of H plus times Hz minus over the concentration of H2Z. And then we're going to find our hydroxide ion concentration. And from that, we're going to find our pH, right? So then part D, pH of a solution containing 0.063 molar of sodium Na2Z, right? And 0.082 molar NaHC. Okay, so we have got an acid. This is our acid right here, and this is the salt. And so we're going to use the Henderson-Hasselbalch equation on this one, right? So that is going to be our pH is going to equal, and he actually breaks it down up here. This is the great thing about this. If you know that this is Hz minus and this is Z minus 2, you can come up here and it tells you that for A2 minus, which you sub in your Z for your A here, A2 minus over HA, we're going to use our pK2. So we're going to come down here. pK2 is plus, not equals, plus the log of our Z2 minus over HZ. And that is Hz minus right there. Okay. And then this is going to give us our pH, right? So on the bottom one, we're given, it's again, we're using the Henderson-Hasselbalch equation on this because we are given two different concentrations of the acid and the conjugate, right, in our problem. So we've got H2Z, which is our acid, and then Hz minus, which is our conjugate here. So we're going to, again, use the Henderson-Hasselbalch equation. And he's gotten it written up here which pK value you use, which a lot of times you won't actually see that. So that is kind of nice that he does that. So we're going to use pK1 for this. So pH is going to be pK1 plus the log of HA minus is going to be our NaHZ over, let's see, what is that, H2Z, right? Remember, our sodium is just going to dissociate, and then we just pretend like that's not there. But if you just remember those rules, that you have to look at your reactions to figure out what to do with your equations. If it gives you the intermediate species, like it does here, and only the intermediate species, then you're going to use the pH equals 1/2 of pKa plus pKa2, pKa1 plus pKa2, right? And then if it gives you just one concentration of either the base, like the, your base here, your conjugate base here, or for here, this is your straight acid. If it gives you just a concentration for that, you're going to use your Ka or Kb calculations, your Ka calculation, to find your pH through the hydrogen ion or hydroxide ion concentration. And then down here, the Henderson-Hasselbalch equation. So those are just a few little quick guidelines on how to figure out which equation to use. If you know which equation to use, then it's just plug and play and you'll do fine.